frames. The first part is translation. Okay, so there's some vocabulary in this course which will be clear once I finish drawing this figure. So we always have a fixed frame or a frame which is fixed to the ground. This frame does not move. So this is a fixed frame. And then there is another frame, which is the frame which is going to move. And so let me show it with, I call it O1, X1, Y1. Okay, and most of the time we are interested in motion with respect to the fixed frame. So if there's a robot moving around, you want to describe the motion of the robot with respect to, say, one of the corners of the room or something like that. That's the fixed frame, the corner of the room. Okay, so let's say that there's a point C. And there are two ways to describe the position of that point. One is we can describe it with respect to frame 0. So let's call this XC. This is YC, the Y coordinate. And what I'm going to do is I'm going to put a superscript 0, which just indicates that the position of the point C here is measured with respect to frame 0. Okay, we can also describe the position of C with respect to a moving frame, which is in this case the frame 1. So here we have Y, C, X, C, but I'll put a superscript of 1. So always in this course, when you see a superscript, it will be used to denote the frame about which I'm describing the motion. So C will have, in this case, two ways in which you can write its position. One with respect to frame 1, other one is frame 0. Let's also draw the position of frame, the origin of frame 1 with respect to frame 0. So that will be the position of O1 with respect to OO. So let me draw this, call that X0, and then Y0. Okay, let me not put any superscript here, just to make it simple. Otherwise, I would just call it X00, and it just won't add much value. Okay, so the notation we'll be using is C0 is going to be the position of point C in frame 0. So this is two-dimensional. So we'll have X, C0, Y, C0, and that's the position of C with respect to frame O, XO, YO. Okay, we can also write C1, which is going to be the position of point C with frame 1. So XC1, YC1, position of C with respect to frame O1, X1, Y1. Okay, so we keep doing that. We write the position of O1, which is the origin of frame 1, with respect to frame 0. So that's this, that's going to be X0, Y0. So position of O1 with respect to frame OOXO YO. And we can also write position of frame 0 with respect to frame 1. So this is basically telling what's the coordinate of 0 when you look at from O1. So that will be simply negative of x0, negative y0. Okay, so position of O with respect to frame 1, x1, y1. Okay, so that's just how translations are described. Let's get to rotations. And this is where it's a little bit, harder, I would say. But then once you get the hang of it, it becomes much easier to use it. So let's get to translation. Okay, so the same, pretty much the same caricature. That is, we start with a fixed frame which does not move. O, X, O, Y, O. But this time, instead of translating the other frame, we rotate it by an angle theta. So when we take a frame O1, which is right now on O, and we rotate it by an angle theta, the new X would be at an angle theta with respect to x0. And since the y is also going to rotate by the same amount, we'll have y1, and this angle again is going to be theta. Okay, so now we're again doing the same thing, which is describing the position of point C with respect to frame 0. C. So what we'll do is we'll find the position of C with respect to frame 0 and also frame 1. So let me just move it slightly to the right. This figure is going to get pretty cluttered. Okay, let's see. Okay, so we drop perpendiculars to frame 0. And we also drop perpendiculars to frame 1. Okay, and let me write down the position of the y position of C. That's going to be y C. But since this position is with respect to frame 1, I'll call that yc1. And then since this is going to be the position of the x position with respect to frame 1, I'll call that xc1. And similarly, I can write same thing for xc0 and yc. Okay, so now that we wrote that down, let's try to express the position of C in frame 0. Okay, and we'll try to do that in terms of frame 1. So we want to find a relation between xc1, yc1, and xc0 and yc0. So for xc1, this is just a trick thing to find the position of this point, which is basically this distance. All you have to do is take this xc1 and project it on the x0 axis. So when you project that by an angle theta, you should get xc1 cosine of theta but that's just hold on, I did an error here. This is not right. Okay, so this is basically going to give me all this, right from here all the way to here. But xc1 is only the distance from this point to this point. So I need to subtract that out. And the way I subtract that out is I can use the fact that if this is yc1, then this is yc1. And if that is yc1, then yc1, which is this, sine of theta will give me the distance which I need to subtract from xc1 cosine theta. Okay. So this gives me a formula for xc0. We can do the similar thing for yc0. Essentially, you're finding this distance. And the way you do it is you again, sorry, my bad. I'm sorry, I'm going to try to find this distance, right? Yeah, this distance. So to find this distance, the vertical distance, I need to project xc1 along the vertical. So that will be xc1 sine of theta. This is theta. And then that effectively gives me not the full distance, but only the distance from this point all the way to the projection on x1. And I need to find the other one, which is the distance from x1 all the way to x0. And that can be given by projecting yc1 along the vertical. So that formula comes out to be xc1 sine theta plus yc1 cosine theta. Okay, this is probably better off if you draw separate figures and try to express it. Here is how I can write this same formula more compactly. xc0 equals a matrix times xc1 yc1, and that matrix is cosine theta minus sine theta, sine theta, cosine theta. Okay, yc, so the question in the chat, y0c is written in the wrong position. Let me check that. yc0 is, yeah, that's right. So this is yc0. Good catch. This is xc0. Okay, so what I can do is I'll denote this xcyc as c0 equals, I'll have a special name for this matrix. I'll call it the rotation matrix. And it basically helps me relate frame 1, right, with frame 0. And then the position of point C with respect to frame 1 is C1. Okay, so that's going to be how I will effectively denote rotations in this course. This will come again and again. Okay, you could also do the reverse transformation. You could write xc1 yc1. So you can do this either using trig like I did, but here you'll be projecting everything on the O1 x1 O1 y1 axis, or alternately what you can do is you can actually invert this R matrix. If you do that, you'll get cosine theta sine theta minus sine theta cosine theta x c0 y c0. Okay, there's a question. It shows the naming of superscript and subscripts given, like what is reference to what frame. So naming, the convention is basically you always have a variable. This is the point of interest. So that will be something on the figure. So point C, point P, point D, and then you'll have the frame on the top. Is that clear? This is what we're going to follow throughout. Okay. Okay, so this transformation which I wrote down here is actually C1 equals a rotation matrix, and just like we have R1 with respect to frame 0, we'll call this R0 with respect to frame 1. Okay, now a few things to note over here. First one is that if you observe carefully, you would have seen that R10 is nothing but the transpose of R01. Okay, because when you take the transpose of this term, you get this term. Okay, there's another property of rotation matrix, which is that R10 times its transpose is the identity matrix. And that's basically saying that the magnitude of the rotation matrix is essentially 1. It only rotates objects, but it doesn't scale them, doesn't make them bigger or shorter. Okay, so that's a property of rotation matrices. What you can do is, now with this property in place, you can multiply both sides by R10 inverse, and you would get R10 transpose equals R10 inverse. Okay, and then if you put that back into the first equation, then you can see that R10 inverse is the same as R10. Sorry, yeah, or that's the same as R. Hold on, there's an error here. Let me say this again. I can't quite put that here because if you see that this is R01 and this is R10, so they are not. You can't just switch them. So let me rephrase this. Okay, the property which you should remember is not this, but these two things. So this is one of them, and this is the other one. You can't do more than what I was trying to do. So this is what stays. So if you want to find if you're given the rotation matrix from frame 1 to 0, then you can find the rotation matrix from 0 to 1 using the first transformation. And then if you want to find the inverse, which is sometimes for a big matrix, for let's say a rotation matrix, in this case 2 by 2, but we look at 3 by 3 matrices where the whole matrix is going to be populated. And if you wanted to find the inverse, the easiest way to find the inverse is to actually take the transpose, which is a neat method because you don't have to do complex transformations and manipulations of the matrix to find the inverse. So those are two properties which I think are useful. Okay, so one final thing before we get to manipulators, which is we want to look at what happens when we do combination of rotation and translation. Okay, so this is the last part 3. Combined translation and rotation. Okay, so here I'm going to start off again with my base frame. Okay, then the moving frame O1, X1, Y1, you can think of it as sitting on the base frame, on the fixed frame O0, X0, Y0. Then we translate it by, say, a fixed distance to the right and up. So let me call that O1, X1 prime, Y1 prime. Okay, and so it's translated by a distance of y 0 and x 0 on the x-axis. Okay, thereafter, what I'm going to do is I'm going to rotate the frame O1, X1 prime, Y1 prime by an angle theta. So X1, Y1, and the rotation is by an angle of theta. And now I'm going to try to look at or try to figure out how I can describe the position of any point C on the which is basically described by in two ways. It can be written in terms of O, or it could be written in terms of 1. Now, one of the advantages of this whole process of writing in terms of a frame, a local frame or moving frame 1, is that it's much easier if you can describe the motion of point C with respect to frame 1, because we know how frame 1 is related to frame 0. So in all cases, in all parts of this course, we'll basically be using this thing. That is, if there's a robot and the robot has, let's say, an arm, and that arm is moving, and we want to describe the motion of a point on that arm, which is this point C, then we can describe that point C with respect to the robot. Okay, that's the robot is in this case frame 1, but we also know the motion of the robot with respect to the ground frame or the fixed frame, which is one of the corners of the room. And so by describing motion of any point like the arm with respect to an intermediate frame, we are much easily able to describe the movement of the manipulator in this case. So what we do here is we know xc1, yc1. Okay, and then we are trying to find how how C moves with respect to frame 0. So what we have seen in the past in the other two sections was we could pretty much write position of C1, 1, 0 with respect to, in this case, I'll call it C1 prime, right? This is, so we know the position of point C with respect to frame 1, but we want to find what its position with respect to this frame. Okay, this is position of C in frame 101 x1 prime y1 prime. But then we also know how to find the position of point C1 prime with respect to 0. So that's going to be C0 equals x0, or rather O10 plus C1. So in other words, what we have here is C0 equals O10 plus R10C. So the position of point C in frame 0 is nothing but translation, and then that's rotation. So we decompose that motion into two parts, which is translation and rotation. Sometimes we don't have translations, like we've seen in the earlier part where we only had translation, only had rotations. But this is a more generic form which we can use. And the two things I described earlier are special cases of this particular formula. And this is a formula which we'll keep using it, which is saying that if you want to find the position of C, you first want to find its position with respect to frame 1, which is this part. And then you find what is the position of the origin of frame 1 with respect to frame 0 using the translation part. Okay. Any questions on that?